speaking on, I've been working, Edith mentioned, I've been working on PCPs for quite some time, and one related combinatorial object is locally testable codes, and we don't know how to construct optimal locally testable codes. It's an open question as do they exist locally testable codes. So this whole talk is motivated by the following question. The question is, do there exist codes that have constant fractional distance, constant rate, and testable with a constant number of queries. I'll define this formally what it means, and we don't have codes. We don't yet have codes. This the whole talk is motivated by this question. We want to know if there exist codes which have all these three properties. We'll see shortly we have codes which satisfies any two of these three properties, and what I will be doing is an approach to potentially construct codes which have all these three. So construct good locally testable codes which have all these three features. So if you can relax any, we know how to do this. If you can relax any one of these constant to subconstants, then we know how to do this. By the way, this is joint work with Yotam Dixtein, Irit, and Noga Ronsevi. So just a quick primer on what's a code in this one. So I'm looking at, so a code is just looking at some collection of, it's some subset of sigma to the n. Typically, for most times the sigma which I'll be talking will be f2, 0, 1, and particularly we'll actually be interested only in linear codes. It's C is a, so in which sigma is a some finite field, and C is a F space, is an F vector space. We'll be looking at this, and a couple of things that I want to mention about one properties. So I'll mention the first properties. So this code, n will be, n is usually referred to as the block length of the code. We're talking about k, which is the in the case of DMA, it's a dimension of C as over the base alphabet. And two important properties of the codes are what is called the rate of the code. So RC, this is the amount of information packed in each symbol of the code, and the other one is distance of the code. Which is DFC is the minimum distance between Hamming distance between two distinct code words. So you're taking two elements of the code, two distinct elements of the code, and find the minimum distance. This is Hamming distance. The number of locations they differ on, and we'll talk about typically fractional distance, which is delta C. I'll just normalize it with n. And what we're interested, the classic question in a code C is a good code. By the way, whenever we talk about a code, I'm not going to talk about a specific code, but a family of codes. That is, we will fix the base alphabet and talk of families of code as n keeps growing larger and larger. So we'll say Cn is a family of good codes if R of Cn and delta of Cn are both greater than epsilon, which is bounded away 0 for all n. That is, you have a family of codes such that all of them have have at least a constant rate and constant. So that explains the first two this one. That's what I mean by constant fractional distance and constant rate. And by now we know that there exist good codes. It's still open as to what is the right trade-off between these two parameters. What's given a particular delta, what's the R? This is open for every alphabet. We don't know what is this. But what? So it's open to get the optimal trade-off between R and delta. So what we'll ask is, I don't care about optimal trade-off between R and delta. We're going to add yet another feature to the code and ask this question is, do there exist good codes that are also locally testable? Okay. Feel free to stop me and ask questions. So what is locally testable? So testable comes from this one. So we think of this code word as a huge. So think of n as a large. This one. Okay. So you have this code word. So you have this element of code word. This is some c, which is c1, c2, cn. It's a long string, and you want to check if this is a valid code word or not. But you don't want to invest time. Typically, if it's a linear code, all you need to check is if it satisfies some linear constraints. And certainly, it's easy to do that if you're allowed to look at the entire code word. The code is specified by, if it's a linear code, it's just a member of some vector space. If you have an explicit representation of the vector space, given the code, it's easy to check if it's this one. What I want to do is actually want to be able to check it locally. I want to distinguish. I want to ask the question, is C, or let's take an arbitrary word. So C, say W1, W2, Wn. So W is some element of this one. We want to check is W a code word? And I want to do this in a very local fashion. I want to look at W only at a few locations and tell with high probability not whether this is in fact the case. So we'll define the notion of what a tester is. A tester is some algorithm, a randomized algorithm T, that based on, it tosses a few random coins, and based on these coins decides to probe, I'd say a few locations, say T locations. And then based on this, looking at the partial view it sees of the local view it sees, it decides to accept the code word or not. So tester is just this object. It's a randomized algorithm. Question? Yeah.
It's not adaptive, or can we see W1, see it's 0?
So it can. So the way I've defined it, it could be adaptive. But if you're working with linear codes, we can show that adaptivity does not help. One might as well assume it's non-adaptive. In fact, come to that. So it's a randomized algorithm that makes less than or equal to T queries into W, and then accepts, rejects. And what we want of this is, if W is in fact a valid code word, we want that the tester, probability of tester actually accepts with probability 1. And if W is not a member of the code word, we want it to reject. But notice that this is too stringent a condition, because it's, suppose T is making just few locations. If I flip W a code word at just one location, you won't be able to tell a valid code word from an invalid code word. So we won't be able to distinguish code words from non-code words. What we'll instead be able to distinguish is code words from things that are far from being code words. So what I would want is the probability that this rejects should be at least some alpha times the distance of W to the code. So things that are further away from the code word should be rejected with larger and larger probability. So I'll call these the two properties I want of the tester. This is going to be completeness, and this is soundness. And for linear codes, we can always assume the tester is, so without loss of generality, assume T is non-adaptive. In fact, furthermore, it's not hard to see that the only thing that T can do is use the random coins to pick a few locations and check every possible linear constraint that is supported within these locations. It checks if those are satisfied or not. If it's satisfied, it accepts, otherwise it rejects. That's all that for a linear code, that's all a tester can do. So it just looks, so essentially it's going to pick some dual code word, some constraint from the dual code word, or picks a few locations at random based not in correlated fashion, and checks every constraint that is supported on those locations. Checks if those are satisfied. If they are satisfied, it accepts, else it rejects. It's not hard to see that any tester is of that form. Now what we want, what I would like to ask is, so say that C is T alpha testable if such a thing happens. And what we want is C with testable with constant number of queries for some alpha which is bounded away from 0. Okay, is the question clear? This is and so this is an extra feature I want to add to the good codes. I want to ask, is there a family of good codes which not only have constant rate and constant rate and constant fractional distance, but are also testable using constant number of queries? Do they exist such codes? We don't know how to construct such codes yet. So what we'll do initially is we'll see how actually good codes, some approaches to construct good codes, and see if those approaches could be modified actually to also yield good codes that are locally testable. So any linear
clarification regarding the test. Did you say you query some locations and then you run every test that all like T local locations satisfy in the linear code, all linear constraints that?
So you can assume without loss of generality every tester is of that form. That is, you give me any tester, you can always convert it to another tester which makes the same queries as the other tester, but then runs all linear tests which are fully supported within the queries made by the original tester.
Oh, that are fully supported.
The fully supported, yeah.
Yeah,
Fully supported, yes. Yes.
So if I'm relaxing, let's say the number of queries not to be constant, but could float n. So what is? Do I know good codes which have logarithmic number of queries?
Yeah. So we do. We'll see this. For example, we will see like Reed-Muller codes and all do have. So they will. So we do know codes which if we do know codes which have these two properties, but are testable with slightly super constant number of queries. In fact, each one of these three, if you relax one of them, you have the other one with a slight super constant. If you replace that constant by super constant or sub constant, these are fraction number. Two of them are sub constant, one is super constant. If you will be, we know how to construct such codes. Yes, and I'll come to that in a short while. Any other questions? So given any code, a code can be specified. So let's look at a code. A code is some, so I have C which is some element of, let's just like take the binary alphabet, so C1. So let's write the code word elements. This is a set of size n. These are the n locations. And I'm going to put C1, C2, Cn. Because it's a linear code, we can assume without loss of generality, it actually, the code is fully specified by a set of constraints that is the code is, these are, this is another, say, M, which I call P, which will be obvious. I'm going to call it. These are this one, and these are basically, it's what's telling you here is this is, it tells you that this code word should satisfy some constraint specified by this vertex. This code word should satisfy. You can assume that any linear code word is without loss of generality has such thing. These are the code word locations. And this is any spanning set of constraints that define the code. That defines any code. There's a underlying bipartite graph that sort of, there are several bipartite graphs. So you can construct, so you can, given a bipartite graph, you can talk of the code. Given a code, you can talk of there is one bipartite, there's several bipartite graphs which correspond to code. So what we'll ask now is, in fact, we can generalize, we can sort of make this construction a little. So right, what I mean by spanning set of constraints, one set of constraints could be just that this constraint checks that the parity of all these locations. So for example, if the neighborhood of this is 1, 5, 8, this could just be checking if C1 plus C5 plus C8 is 0. It checks some linear constraint. So each of these correspond to checking some linear constraint. Yes.
What if you do the applet size is bigger than 2? You just have like one vertex for C1, for 2C1, and so on.
So yeah, so it will be some linear constraint. So we'll generalize, in a minute I'll generalize this a little more. What we'll say is each one here itself will be specified by, so let's assume the degree over here is say D. We'll specify each one here itself by a vector space in sigma to the D, and all that's saying is this local view should be a member of that vector space.
But there's no graph anymore.
Huh? It's a graph and this, so it's specified. So this is what they call the Tanner specification of the code. It's a special case of what you're talking. I'm going to say I'm given a bipartite graph G, and that's the left side, the right side, and the edges, and I'm given a base, and let's assume this is D left regular, D right regular. And let's base C is a base code, C subset of F2 to the D is a base code. Then the code specified by both this graph and my G's and this one are, how do I write? Is basically the set of all C in F2 to the N, such that for every vertex here, its neighborhood lies in the small code. So for all U in T, the C restricted to the neighborhood of U is a member of C naught. It's a very nice, every code has this nice form. This is called the Tanner code corresponding to this. And we can ask, is there a property of G and the base code that will guarantee that the larger code? So G is sort of a large. C naught is a small, if D is constant, C naught is a small sized object. We can ask, is there a property of family of graphs G and the single base code C naught such that the corresponding family of Tanner codes that I construct have the properties that I want? I'm just asking. So is there a property that G and C naught satisfy that implies C of G C naught is a good code. Yeah. Huh? Base code is just a smaller code. It's just so there is a small code here. Each local view over here is stating that its neighborhood, this local view should be a member of C naught, and I'm building up, for example, out here, the members of this view is just all those local views whose parity is 0. So it's just a code on this small neighborhood. It's on this, it's a code whose block length is D. So
for these base codes, is like are you always going to have like a 0 on the right hand side of the equation?
Okay, you want 0 to be a member of the code, right? It's a linear code.
yeah.
That's
Yes.
why D is the length of the constraint.
Huh? D is the length of the constraints. D is the length of the constraints. D is this regularity from this side.
So the most natural one that people started looking at is when you just do the XOR, so then the base code would have code dimension 1, just all vectors that XOR to 0. And this is a slight generalization. You can say, oh, maybe it will have more vectors, just they need to belong to some specified subspace called C0.
So I'm just generalizing. Here the subspace C0 was just all even vectors. I'm just generalizing that to a slightly larger family C0. That's all. So we're given a graph, we're given C0. So for this I would have to want the graph to be, say, left regular, and I have a single base code C0, and I'm asking what are all the members of this, such that we will see, I'll shortly see examples in which C0 is not just the parity code, not just this code, a slightly generalization of this, for instance, in which you can still have a family of such codes. We ask now is, let's relax our question. Let's forget about constant number of queries. Let's just ask the constant fractional distance and constant rate. I want to ask, can I construct codes in this process? So now constructing a code means to construct this graph and the base code such that the corresponding code which I have constructed, the Tanner code which I have, has good rate and good distance. And what Sipser-Spielmann showed is, in fact, at least in the early 90s, is they showed if G is a bipartite expander, then, I'm just writing informally, then the corresponding Tanner code GC0 has distance, rather sort of inherits its distance from C0. Sort of, you have a small code which has good distance, and sort of G, which is a larger code, inherits the distance from this code. So the problem of constructing a good code has now sort of, and so you need to just search, you need to come up with a family of, so previously what did we want to do? We wanted to construct a family of codes which had these nice properties. Now instead of that, what we need to do is construct just one base code which has a nice property. You can do it by an exhaustive search, and a family of expanders which have nice properties. We want a growing family of graphs. So we sort of transferred the problem from constructing a family of codes to a family of graphs. If you have a family of graphs and one base code, then I have a family of codes which have good distance. Yes.
These are one-sided expanders, like it's a subset of the guys on the right have large neighborhoods.
Yeah, so the expanders they wanted was, in fact, what they want. So they wanted was every set here has a large neighborhood.
Oh, okay.
Every set here has a large neighborhood.
Just that. The point was that you can also decode, not just to construct these codes. The Sipser-Spielmann point was that they can also have a decoding algorithm.
Yes. And one second, I wanted to add, this is just talks about this one, and the rate of what then the rate of, let me write it this way, if size of if m times d minus the dimension of C0, that is strictly smaller than n, then the combined code has rate, good rate. How far, the gap between these two will determine how good the rate is. Let's ignore. Basically, I want d minus dimension of C0 is the number of free variables for each this one, that's multiplied by m, that should be less than n. M is the number of constraints on this side.
D minus dimension of C naught is the number of constraints imposed by one vertex.
No. D is the it's not the number. It's the
It's the number of constraints imposed by one vertex.
yes.
Right?
M is the total number of constraints. These number of constraints, as long as they are less than n, it says that you still have this.
What is the number of vertices on the right hand side here?
Yes. So it says as long as the total number of constraints is not. This is just a trivial bound. There might be other cases. If this happens, then you know that the total number of constraints imposed is less than the dimension of this. Hence, there will be rate surviving in the code. This is not the only. The main, this one of Spielman was, if you had a good expander graph, then, and the base code was had good distance, then the corresponding Tanner construction also has good distance. It inherits the distance, and furthermore, they accompanied this with a decoding algorithm. They showed that if you give me a sort of corrupted code word here, you can correct it in linear time. Get this.
Sorry, what rate does the new code have?
The new code will have rate n minus this quantity by n. At least that's the rate is at least that. So these are the number of the code is specified by so many, at least at most so many constraints. Therefore, the dimension of the new code will be at least n minus this divided by n. That's a lower bound on the rate. The rate might have better rate than this.
You can concentrate only 0.929.
Huh?
You're saying that should be 1 minus epsilon.
Yeah, this should be a 1 minus epsilon. This should be, you want this to be bound. That was my less reason for you. Now we can ask the same question. So this sort of transfer the problem of constructing good codes to constructing good by expander graphs. If you have good expander graphs and a nice base code, it tells you you can sort of inherit, you can get a good family of codes just from this. Now you can ask the same construction actually lets us add this extra feature, local testability. That is, can I have this graph over here? I have a graph. Can I show some properties of this graph such that the same construction actually is not just a good code, not only has constant rate, constant distance, but is also testable with constant number of queries. And in fact, when you have such a graph, there's a very natural test associated with it, which is just pick a random vertex on the left and query it and check if it's a query if that local view is a member of C naught. In fact, we'll ask further this question is there a graph such that this natural test, the corresponding Tanner code is testable with this natural test defined by the graph? Is the question clear? And sort of this is sort of we have a result, old result with myself, Eli Ben-Sasson and Sofia Rashkodnikova, which said that if G were a random graph, random bipartite graph, then the corresponding Tanner graph, Tanner code CG C naught is not locally testable.
You're always assuming the right side is smaller.
Huh?
You're always assuming that the right side is.
I haven't assumed it so far. For Spielman to have good rate, the right side has to be smaller. For their distance, this one, it doesn't have to be. For their distance amplification, for their distance preservation, it doesn't have to be. But to show that they have a good rate, this is the condition they impose. We will be relaxing this. We will be getting out of this constraint, right? So it's a random bipartite graph, which is in fact, we'll show that is most one. Yeah.
Just related to this theorem. So if it's very in this theorem, is it small or?
In this theorem, it is small. This theorem is exactly the setting of that Spielman case.
But if it's small, isn't it always the case? There's just not enough parity. There's not enough checks. Somehow there's no redundancy. that is it true for any graph if it's small or?
I don't see how to show it for any graph, because every graph, it's clear that the natural tester will fail, but the claim is not only in a natural tester. This is not LTC for any tester, not just by the natural tester. Yeah. Yeah, I can show this. So sort of just this approach, just take a graph. So and a random bipartite graph is a good expander. So it will be a code with good distance according to the Spielmann, this one. But what this theorem says is actually, even though it's good testable, it actually is not testable, not just by this natural tester, but by any tester. So we possibly need some other properties of the underlying graph if you want this construction to go. And that's what the sort of main result which we're going to show is, we'll show that if this graph had some further properties to it, and then we can actually show that the underlying code is locally testable. Questions? So far? So before we get to what the property is, going to be quite a while to tell me what the properties of the graph is. What I will do is I will describe examples of two known locally testable codes which don't have all the three properties, and then come to, yes.
Random, you mean random deregular?
Random deregular.
It will be an expander.
It will be an expander. So it will be an expander. So it will be a good code with good distance and good rate, but it will not be locally testable by any tester, not just the natural tester. In fact, more or less, the proof more or less shows that if it uses actually expansion of a very closely related graph, not just this bipartite graph, it shows a related, because it's a random graph, certain related graphs are also expanders, and because they are expanders, that's what will come to show that this one is not locally testable.
So the natural tester in this context is sample a random right vertex and then do the test on the
Yes,
user?
yes. Okay, let's see two examples of locally testable codes. And both these examples will sort of go to this point in which the right hand side no longer will be. So far, to get rate, the right hand side had, the way we set it up was always m was much smaller than n. Both the examples I give you, they will be examples of codes which do have rate, but yet m will be much larger than n. So we won't be able to be proving rate using this condition, but we'll be proving rate separately for these codes.
How large should we think of D as?
So that depends. D, ideally I would like D to be constant. The two examples I'll see, one of them D will be 3, other will be the field size itself, will be slightly larger. So we'll see a couple of examples. So one will be what I'll call the Hadamard code. So here, the set of code words, it will be easier to view them not as strings but as functions. These will be functions themselves from f2k to f2. So in other words, each of them, each f itself is function from f2 to f2 to the k. So the block length, it's 2 to the k for one, such that f is linear. That is, f of x plus y is f of x plus f of y for all xy. What's this code? This code, one way of the sort of one Tanner representation of this is have f2k on, right? And what I'll give out here will be corresponding to, in fact, every triple of the form x, y, x plus y. So this will have x, y, x plus y, and you query those three locations. So notice this is one in which the right hand side is much, much larger than left hand side. Right hand side, this is f2 2k. and that's sort of the graph defined by this code is exactly the Hadamard code. And it's non-trivial to show that actually this is a natural test for this code. This happens to be a natural test for this code. This is the result due to Blum, Luby, and Rubenfeld. We show that. A natural test is a good test for her. In particular, it will obviously it accepts all strings in the code word. If something is delta far from it, it will reject it with probability proportional to delta. So it's in the sense this code has, if you look at two features of it, it's testable with constant number of queries. It's not hard to see that the distance of this code is half. Any two linear functions will differ in at least half the locations. So the distance of the code is half. What it fails miserably is the rate of the code. The rate is inverse exponential for this code. Okay. The other example of example 2 we'll see is what we'll call Reed-Muller codes. Here, we'll work with some underlying field, finite field. Think of this field as a field. I'm going to change. M is going to be the number of variables, and there will be a degree parameter. D is the degree parameter. So out there, Hadamard code was the set of all codes from F2k to F2 that were linear, this one. So it's the evaluation of all those one. The Reed-Muller will be just a very natural generalization. In fact, Hadamard code is a special case of the Reed-Muller code. Reed-Muller FMD is exactly those functions from Fm to Fm. Fm to F, so that F is a evaluation of a degree less than or equal to D polynomial. So it's a some polynomial. So that was a special case in which F was a linear polynomial. This is I'm going to allow all the way up to degree D. And degree, when I mean degree, I always refer to total degree. So this also has a very natural graph representation. Let's look at the case in which, say, f is the size of f is larger than D. So the left hand side is once again Fm. What I can do on the right hand side is I'm going to put in. So we're going to use the fact that if you, in this case, what's a Reed-Muller code? I'm given some space Fm. I'm saying this, I'm giving you for every point in the space a value, and I'm claiming that this is the evaluation of some low degree polynomial. Now, if in this particular setting, if f is larger than D, if this is the evaluation of low degree polynomial, if I restrict it to any particular line, that will also be a low degree polynomial. So what I'm going to put on the right hand side is a set of all lines, and each of them sees size of f points, and you can say that this restriction should be a low degree. What each line should see should be the evaluation of a univariate polynomial. So in that sense, this is sort of a lift of so this is all these univariate polynomials are also called Reed-Solomon code words. So in some sense, Reed-Muller code words is the lift of a Reed-Solomon code word for some setting of parameters. Also, what I will call Reed-Solomon code. So every local view is the evaluation of a univariate degree less than or equal to d polynomial. Okay. Yeah.
Is the evaluation kind of a decomposition of the polynomial?
In the sense,
Like if it's a multivariate polynomial,
yes.
are you kind of decomposing them into a product or something?
No, not necessarily. It need not be. It just says, so it just say if you have a multivariate polynomial, this one, then the restriction to any smaller subspace still, if it's low degree in the large space, it continues to remain low degree on the smaller space. And this is not just a one-way direction; it's a characterization. That is, if it's low, that requires a little bit of work to show that if it's low degree on every small subspace, then it's still low degree on the large subspace, and that's what's been used over here. So Reed-Muller code, something which is low degree globally, if an f say twice larger than d, then you can show that restriction to every line, it will also be low degree. Certainly that direction is true, and I'm claiming that the other direction is also true, that is, the restriction to every line is low degree, then globally also there is a low degree representation as a multivariate polynomial. The number of code words is going to be, it depends on the number of monomials of degree at most d. That will be the dimension of the, it will be the number of m-variate monomials which have total degree at most d. That will be the dimension of the code. Notice both these graphs actually, this side is much larger than the number of lines is quadratic in the number of points. The same thing happened in the other math case. It's not, so we won't be able to show rate using this one. The rate is showed separately, just like out here we counted the dimension of it in a different fashion to get rate. Here we're going to do it. Now what I want to ask is, can I sort of generalize these two to show that in cases it's not hard to see that these underlying graphs is actually a very good expander. These are not random expanders, these are expander graphs. So in some sense you can prove distance of these codes via the same Spielman, this way using the expansion of the code. You won't be able to show test. The question is, what is there a property of these bipartite graphs that actually make them testable? What we'll see is actually to identify one property. We'll show that if this graph was part of a larger object was part of a larger graph which had more properties, then we will show that the underlying code is locally testable. That's going to be the sort of nature of our result. Before we're going to have graph n. This is going to be a set of constraints T, which I'm going to think of some subset of n choose T. So this is going to be and we have some base code C naught, which is say f2 to the sigma to the t. So there's a base code sitting over here in each of these. And I want to ask, is the corresponding the final code which I want to care about is going to be the lifted code. It's going to be the code defined by this graph in TE and C naught. I'm going to ask, is this code testable? Sure. The result goes, suppose this graph is a part of a larger graph in which there were more layers to it. Say this was what I'm going to call k layer, which is some subsets of size k, and S layer, which is, think of T smaller than, yes, and we are going to have the most natural the edge constraints are going to be if this subset is fully so these are all T subsets, these are K subsets, and these are S subsets. And I'm going to put edges between them if this subset is contained in the other. So the edges are all edges are defined by inclusion. Was a question? Yes.
So you haven't told us what these subsets are yet. Are they going to be like due to random or something, or?
So I will want some properties of these 4 layers. I'll say if this graph and the base code has some properties, then the lifted code, this will be the lifted code, will be locally testable.
Okay. We don't even know yet how big they are or what they look like, right? Like TK and S.
Huh?
We don't know like TK
I
and S, how big
I haven't told. Think of the ideal construction will be when T, K, and S are all constants.
And you have the whole family, or?
Huh?
And like, what are big T, big K, and big S? Are they going to be the entire?
No, they won't be. They won't be the entire. It depends. It will be anything that supports these 3 will have this construct. Question.
Okay.
So since this, I don't yet have a locally testable code, so I'm going to say if there's a graph which has these properties and there's a base code which has these properties, then there's a locally testable code. It's only a conditional statement because I don't have a single object which satisfies all the ingredients yet. Then my main theorem would be that there is a locally testable code which has these 3 properties. What I will show right now is a graph which has these 3 properties and a base code will yield a locally testable code. I don't know if I have a satisfactory setting for all the initial ingredients. So what do I want for the hypothesis of this? The first thing we want is, so there's going to be, I'm going to sort of view this as some sort of, what did Sipser-Spielmann do? Sipser-Spielmann took a small code, C0, which had good distance, and sort of lifted that distance to the large code. We'll sort of do a similar thing. We'll take a small code, which is locally testable, and lift it to a large code, which is locally testable. And what is the small code? So I want this. So look at these S sets over here. Take any S over here. So given an S, we can construct this bipartite graph. So for all S in S, we can construct the bipartite graph GS, which has as its left hand side just the set S, that is just the elements of that, just the S elements of the S subset, and all T, all constraints T, such that T is fully contained in S. So just look at the restriction of this, of the first 2 layers to the subset S. Restriction to those coordinates which are fully contained in S, and those local views which are fully contained in S. That's the graph I'm looking at. So it is T restricted to, yes, it's the corresponding, it's this graph. Is this graph clear? So for every subset here, I can look at the corresponding graph over here. For example, the easiest way, one natural realization is sort of this comes from, take the points, lines. When I've drawn this line, I can add one more layer to this called the planes, and 4-dimensional this one. So for every plane, I'm looking at just points in the plane and the lines that are contained in the plane. So for every S subset here, I'm looking at just those coordinates which are in the S subset and those constraints which are fully contained. So this defines a smaller part of the initial bipartite graph. You can ask if this code, I want this code, the code CS, which is the lift of GS and C0 is locally testable. So it's this is a.
So it's everything you can reach from S by just walking left.
Yes, just by walking left. So from S, you just look, it's this whole, it's all in this. That comes a single. Okay. What I want is this object is locally, is say alpha locally testable by the natural tester. That's the second thing is I want the structure N T K yes to have the following property. One, this, if I just look at the graph T and K, the graph between these two layers, that should be a good bipartite expander. Let's say spectral gap lambda. We'll need some requirements on lambda. I'll come to that shortly. And then you look at the this graph, N, K, and S. That is this layer, this layer, and this layer. This should be what I will call a C agreement expander. I'll define this shortly. Lambda less than lambda should be conclusion. The large code C naught is locally testable by the natural tester. Huh? C without the naught C. This C. Yeah. So this should answer your question. So we do have graphs which have all these three properties. What I don't know is if there is a base code C naught or that the smaller lift. So what is, let's look at, I'm yet to define what an agreement expander is. I'll have 5 minutes to do this, I'll defer this. But what do we have right now? I'm stating that if there's a base code C naught, so that its small lift, its lift up to subsets of size S is locally testable. And this larger graph has some properties. Then the big lift, the lift all the way to N is actually locally testable. In some sense, if you want to look at it from the Reed-Muller case, it sort of says if the lift to planes is locally testable, then the lift to any dimension is locally testable. If there is a base code such that the lift to one object larger is locally testable, then it is testable to any larger dimension. So it says if a small lift is locally testable, then a large lift is locally testable. So it sort of reduces the problem of finding locally testable to one small code so that the small lifts are all locally testable. Questions? Sorry.
Probably I don't understand something of the parameters, but if let's say all the S is a fixed size,
Mm-hmm.
then GS is not really, I mean, can't you just locally test it, just test whether you are in the actual code?
I want it to be testable by the natural tester. So it's this hypothesis is it's testable by this tester, the tester which picks a particular element in T. Yeah, so I want it to be testable with this natural tester. If that is testable, then I will be able to show that look, this one is testable. Yes, it's a constant size code. So certainly it is locally testable by looking at not that tester, but by this tester. Yeah.
Does it have to be locally testable because alpha that's dependent on other parameters?
Not alpha. So the final so what I'll get is the alpha here will be a function of the alpha, so alpha, delta, and lambda.
But the only condition is this lambda is at most.
The only condition is lambda is at most the distance of the base code, alpha, which is the testability of the small code, and C, which is the agreement parameter. So if lambda is smaller than all of these quantities, then this one will be locally testable alpha prime, which is some other function of this. So as long as all of these are constant, this will be another constant dependent on that. Alpha prime is some alpha prime of alpha, delta, and C. Yes.
So you don't require anything between n and t part.
I don't require n and t, but for the graph case, I don't require. Eventually, I would sort of require in the sense that all of this shows only local testability. It doesn't show that the underlying graph has good rate at all. It's conceivable that in the rate conditions, there will be something that goes on there. This completely avoid this. Right now, I don't know how to show. I don't know of a C naught that satisfies these properties. So forget about. I don't know about this.
The other thing as well.
Yeah.
It's the right moment, but both these two parts, so have both k and s. So first I guess you use k to do expansion, and then judging from the properties, and then you somehow do.
Yes. Yes.
But
Let me actually get to the agreement thing, and then we'll come to this. I'm already sort of. What do I want? An agreement expander. I have n, k, and I have s. So this is some subset of n choose k. This is some subset of n choose. Yes. What do I want of this? So want some local to. So we want this. I'll say this graph n k s is a C agreement expander. If the following hold goods, if for all local ensemble of functions, what do I mean? So I'm going to give a function for every S. For every SI subset, I'm going to give a function on the SI subset. So I'm giving you an ensemble of functions which are local. They are specified only on the set ES. I want to ask, are all these functions actually a single global function? Is it just one function sitting on? Is it just the restriction of a single global function on n? Is it arising from, these are just local views of a single global function. So that for all local functions satisfying, so at the very least they should be locally consistent. So we'll have the following property. That is, if you pick a random k size set and two S and S prime, so I'm going to look at this, a k size set and two S and S prime that contain them. Fs restricted to k and Fs prime restricted to k. These mostly agree with each other. They are locally consistent, say with some probability 1 minus epsilon. At the very least, they should have some local consistency. So two things are consistent this way. That implies that there exists a global function f that explains almost f restricted to S is equal to Fs. Actually, I should write it as not equal to, is less than or equal to epsilon. Then this is not equal to less than or equal to C times epsilon for a random S. So if the graph supports this structure, then I'll call it a C agreement expander. And one such graph, what are examples of graphs that support such structure? If this was all T size sets, all K size sets and all S size sets, then it does support it. The Reed-Muller, if these were set of all lines, these are set of all planes, then we know it supports it. High dimensional expanders also, Ramanujan complexes support it. So we know of various graphical structures that have these two properties. What I want is if I had a base code so that the small lift was locally testable, then this would immediately imply, this would give you a large code that is also locally testable. Any questions on the which graph? An agreement expander. No, there isn't. So when I'm talking about this graph, I am referring to the inclusion graph. You will be able to show it has some. This will force you some expansion properties will be already forced by this condition. Because you do want these things. You want some local. You're saying a local consistency should transfer to become a global consistency, and this will happen only if there's some sort of weak expansion properties. I'm not sure what, but yet you will need. Yes.
What is the random sampling over? Is it all triples Ks as prime, or is it overall K and then overall?
Which come again?
Like this probability over S K S prime. What exactly? What if for some K you see more S and S prime?
Yeah. So this thing has to come with some. There's an underlying. So the way I defined it, pick a random K and pick independently two S and S prime that contain it.
Okay.
Yes.
Meaning that the K is not in very many S and S prime, and the ones that are in there will be more likely to be chosen.
Yeah, but this is sort of a requirement. So if for such a local, those cases will be bad. Invariably, every K will be sort of contained equally many, because you want local consistency to imply global consistency. If there's one K which is going to be contain too many or too often, that's not very useful.
If you make K and S random, will this be good or?
No, so a random thing we don't know how to.
But it should be in some expansion condition.
So in fact, random thing will not. For a random thing to have this property, you will need this to be very, very large. We don't. Ideally, we would like this with K and S being. So one thing to notice: if K were set of all K sets, and the S were all set of say 10 K size subsets, then this theorem is true. What you would like to know is, are there sparser versions of this for which it is true? And high dimensional expanders offer you some such.
It's like a strong pseudo-random property, which you said high dimensional expanders.
Is it a pseudo-random property?
High-dimensional expanders
Are not pseudo-random. This is some agreement expansion. They are not so. It's not a property that random graphs don't have this property. A random. Yeah, so I won't call it a pseudo-random property. It's a random it's a high-dimensional expansion property. Yeah, the theorem was a mouthful. I didn't have time to come to how to prove this, but yeah.
Sorry, could you just clarify? So this is what an agreement expander is. Now, what is it? So is this the assumption you need? Or
This is the assumption I need. So I want the graph to support an agreement expansion. And this sort of the graph to support an agreement expansion. It comes from a generalization. You observed both the Hadamard, this one, and the Reed-Muller. They are all actually parts of larger graphs which support agreement expanders. And this sort of generalizes. So it sort of gives you a unified proof of both these things. Why are they testable? If there's an underlying graph structure in this which supports agreement expansion, if it has it, then I will be able to lift a small code that is locally testable to a large code that is locally testable. So what we do have in this construction, I must say, that we do have graphs, we do have family of graphs which have this property already. This one. What we don't have is, I don't know if there is a code C0 that talks well with this code so that the small lift is locally testable.
And what about the rate of
So I don't know what C0 is, so I don't know what the rate of the corresponding object is also at this point. Yeah.
Do you have like a Sipser-Spielman?
No, because all of these are going to be the right hand. Sipser-Spielman had the advantage that the right hand side was much smaller than the left hand side, so they could just describe rate that way. all of these codes necessarily will have the right hand side to be larger than it. So, such a straight. For example, even Reed-Muller, if I just define Reed-Muller this way, it's actually quite a miracle that any rate survives. That is, if I say I'm looking at all functions that they have a restriction to every line is low degree, it might be that the only thing that satisfies this is the all zeros polynomial. It so happens that there is rate that survives in it. Similarly, C0 should be a nice code that talks well with the graph such that rate survives. I don't know if such a C0 exists. If one exists, then this will a recipe for constructing locally testable codes.
Is there any code construction where you don't believe it can be like completed and explained by this hypergraph expander?
You mean a locally testable code construction that is I think you can artificially you can take a locally testable code, make it locally testable by removing some graph property, yeah, and do it. Certainly you can do that, yeah.